Good evening, everyone. Welcome to the last slot of day 2. We made it. I know you're probably all quite tired after a long 2 days of learning, so I'll try and make this a bit fun. And we've got the cocktail party afterwards, so I'll see if I can finish a bit early so we can get out of here and get to relaxing a bit sooner than usual. I think if everyone's here, we can lock the doors and start looking for clues on how to escape. My name is William Brander. I work for a company called Particular Software. We make N-Service Bus. If you're interested in learning about how to build distributed systems in .NET, N-Service Bus is a framework and corresponding set of libraries to help you build rock-solid distributed systems. But I'm not talking about that today. So if you do want to talk about that, come find me at the booth later or at the party, and I'm happy to talk about it with you. Instead, today, we're here to talk about my crippling addiction to escape rooms. I spend a lot of time in escape rooms. In fact, anywhere I travel somewhere, I try and do an escape room with the people that I've traveled with. It is one of the things that I absolutely look forward to. I haven't organized one in Oslo yet. In fact, I live in Johannesburg, and there's probably only about 2 or 3 escape rooms in Johannesburg that I haven't completed yet. So I need to ration them out for special occasions. I look for excuses to do them, so I now need to kind of hold myself off. Of the 7 continents, I've done escape rooms on 5 of them. There are only 2 left. North America I will be doing in 2 weeks, so I can tick that one off, which just leaves Antarctica. I've got 2 plans for that. One more realistic than the other. The first is to blow up Antarctica. If I destroy it, I've done all the continents, right? The second option is to do a complete change in careers, become a research scientist, get stationed at one of the research stations, and once I'm there, find all of the access control mechanisms I can and throw them out during a snowstorm, thereby triggering a really fun escape room with my fellow research scientists. I'm sure they'll love it. I would, of course, do it at the Norwegian research station, not because I'm in Norway now. South Africa does have a research station there, but the Norwegian research station is known as the Troll Station, and I can't think of a better place to act like that than at something called the Troll Station. Another fun fact about the Norwegian research station in Antarctica, because date time zones don't mean much there, they've got their own time standard known as troll time, which again is the perfect time to do shenanigans like this. Now you might be finding yourself asking, William, why would you build an escape room? And that's an excellent question, because it was a lot of work. And I built it for these 2. These 2 are my daughters, and I absolutely adore them. And they know that I love doing escape rooms. So they asked me if they could go do an escape room with me. Now, unfortunately, in Johannesburg, there's no escape rooms that are at a suitable level of difficulty to engage young children. So I couldn't take them to an escape room because they'd probably just get annoyed, they'd get bored after a few minutes because they can't solve most of the puzzles that are there. I ended up thinking to myself, well, maybe what I can do is I can make an escape room for my kids so that they can go and invite their friends and have a similar experience with escape rooms as I do. Maybe they can start building memories with their friends in the same way that I do. And to do that, I had to think, well, what do I want out of an escape room? What do I enjoy? So I started listing a few things. The first thing that I look forward to in an escape room is the decor. Like, these are absolutely stereotypical kitsch decor escape rooms. The more immersive it is, the better. If you live in a room like this, please come and speak to me, because you must be one of the most interesting people in the world. But this type of decor is amazing for escape rooms. It really immerses me. You can see there's padlocks hidden around the room, some with little combination locks, some with keys that you have to find. There's pictures around the room that are probably clues. This picture on the left-hand side, right-hand side, sorry, it says, "Hell hath no fury like a woman scorned." Again, if you have this hanging in your house, please speak to me. But this one is definitely a clue, because the hell in the first word is written strangely. In fact, it looks a bit like a backwards and upside down 4, backwards, upside down 3, backwards, upside down 1, 1. So I'm willing to bet that somewhere in this room there's a combination lock that will be opened by the numbers 1, 1, 3, 4. And that's the type of stuff that I love. I also really love when there's more than one room in the escape room. So if you finish the room and you get to the last door and you've solved all the clues and you're so happy and you open it and you're presented with an entire new room with new puzzles that you have to discover and explore, that is amazing. It's so great. You're getting double the value for your money. So when I ran the escape room for my kids, what I wanted to be able to run it in environments where there were lots of rooms, and I could use the keys for the doors in those rooms as part of the escape room. Because it was portable, I also wanted to be able to make it that if there weren't doors, there had to be lots of containers and chests that they had to open. So I needed to be able to lock a bunch of different types of things so that they could go and explore. Because when they get into a new room and they see a new set of puzzles, new things they have to solve, that's going to stimulate their imagination. Along the same line, the puzzles that I give them must be engaging. They must make them wonder, like, oh, that is so pretty, that's so cool. Why are there green bottles? Those look so pretty, but there's some in the lid. What do I do with that? They must be stimulated. Their imagination must be triggered by what they see and they engage with. And of course, escape rooms must also be finishable. And I don't know if that's a real word, but I'm claiming it now, so finishable is a real word, even if it isn't. And the thing with being finishable is I don't want them just to be finishable, as quickly as you can. If you finish an escape room in 20 minutes, that's probably too easy, and you haven't been fully engaged with the room. You haven't had your imagination stimulated yet. So for me, the sweet spot is somewhere between 45 minutes and 60 minutes. If you can finish an escape room in that time window, it is perfect. In fact, some of my favorite memories of escape rooms are the ones where you can see a big timer in the room and it's your impending doom. As you can see, you've only got 1 minute left and it ticks down and you suddenly solve that last puzzle and everybody sprints to the front entrance again. That is amazing. I love that in escape rooms. So that sort of gave me my list of requirements that I wanted. I wanted the escape room to have simple puzzles, and when I say simple, I don't mean easy. Simple just means they must be easy for the children to understand, because I don't want to have to sit and explain how the puzzles work. An example of what I mean by this is pushing a button is simple. It's also easy. But if you put that button behind laser tripwires that they have to climb through, it's still simple to push the button, but it's hard to be able to do it. I then wanted the escape room to be finishable. I wanted lots of different areas in the escape room. I wanted to be able to have it in different scenarios so that if there weren't lots of areas, they can open lots of things. And I wanted to give the children a sense of wonder when they engaged with the puzzles. They must be visually stimulating for the children. Those were my absolute must-have requirements. I had a few optional extras that I wanted as well. I wanted some replayability because I wasn't going to go through all of this effort and run the escape room once and be done with it. And to get replayability, I needed to be able to have some of the puzzles be reconfigured in different ways so that they do different things and behave differently so that the children can do them multiple times. Now, out of all of these requirements, the hardest one to achieve for me was the finishable, specifically within that 45 to 60-minute window. And the reason for this is that some children are really, really smart. They're absolutely gifted. And some children they haven't grown into their smartness yet. And designing an escape room for different types of children with different skill sets and different strengths so that they're all finished within that 45-minute to 60-minute window is really difficult. So what I eventually came up with is I needed a way to be able to take the difficulty of the puzzles in my escape room and change it, make it easier or harder as the children were working through the escape room. So if they were taking a really long time at the beginning, I wanted to make the puzzles later on a little bit easier. But of course, I didn't want the children to know I was doing this because that would be a real confidence destroyer. And that's not really what we're supposed to do with children. So let's take a look at some of the puzzles that I made and how we can use those puzzles or change those puzzles to change the difficulty of the escape room. So the first one is a balance puzzle. It's essentially just a little sphere that's got lights around it, and inside there's a little digital spirit level, and they have to get it perfectly level for a few seconds before it triggers. You can also change this puzzle to have it that if you point it at specific targets, it triggers a success. So you could have numbers stuck up around the wall of the room, and if they pointed at the 9, then the 4, then the 2, the combination could be 942 for them. Now, the way I can change the difficulty of this puzzle is by changing how close it must be to the target. How perfectly flat must it be? How long must it be on the target before it registers a success? And the number of targets that you must use. So obviously this wouldn't work if you were using it to show a combination like 932. But if you had it that they had to point it at the sun, the moon, and then the window, you could decrease the number of things that it had to point at before it unlocked the next part of the room. And then, of course, you could change how the object is manipulated. So if you're holding it in your hand, it's really easy to get it to point exactly where you want. But if you're manipulating it like my kids did with strings, and they had to pull it up or down, it's really fun to watch because they get so annoyed with each other. If I was running this for older people, I might have it that there were pulleys that they had to use to manipulate it, so it was even harder for them. That, obviously, you can't change on the fly, but you would choose that beforehand. Another puzzle that was quite interesting was something that I called a musical tone. So there's a button at the top where you push the button and it plays a little song, a tune. Mary had a little lamb or something like that. And then the keypad has buttons, and each button corresponds to a specific musical note, and they have to repeat the song that's played from the speaker. This one is really fun to watch children do because for a change, they're quiet. They're all standing around trying to listen to this thing that's making little noises. Peace and quiet is a wonderful thing with children around. Now you can change the difficulty of this by changing the length of the song. Mary Had a Little Lamb is easier than Mary Had a Little Lamb, its fleece was white as snow. The longer you make it, the more buttons have to push and get correct to get the password. You can also change the randomness of the song. So if it's a song that they know, Mary Had a Little Lamb, it's easier for them to remember that song and listen to it in their heads while they're pushing the buttons. But if it was, in the case where I ran it for my children, the Tetris theme song, they have no idea what that is, and they struggled a bit with that. We've also got the Simon Says puzzle, where there's a few boxes, somewhere between 1 and 5. I eventually made 5 of them, where there's 2 buttons and 2 LEDs on the boxes. And these boxes communicate with each other, and they show a pattern along the lights. So the pattern will be gray, red, yellow, blue, yellow, red, and the lights will flash across the different devices. And the children have to repeat that same combination by pushing the buttons on each device. Children have no chill with this, and as soon as someone got it wrong, there was amazing fights and screaming between them. It was great. You can change the difficulty of this by changing the number of devices that they have to work with. So there were 5 that I eventually made. To make it easier, you could reduce the number of devices that actually take part in this. If there's only 2, it's easier than if there were 5. You can also change the number of buttons. Now, I don't mean physically go and remove some of the buttons. That obviously wouldn't be possible. But when it shows the lights, you can make them only use, for instance, the left light. Because if they only have to remember 1 button on each device, it's substantially easier because they're just remembering their position in the order, not the position and the side that they have to push. And again, you can always change the length of the password. So if you make the pattern they have to repeat longer, it's substantially harder. There's a bunch of other puzzles that I made, but these are the ones that are of importance for us today. So I'm not going to, if you want to hear about some of the other ones, you're welcome to come and talk to me afterwards, but I'm not going to cover them in this presentation. But once you've solved a puzzle, you need a way of dispensing the next set of clues. So we've got a few of those. We've got just a box with a maglock in it, and once they solve something, the maglock releases, and whatever's inside falls out. This works really well if you put it high up so that when something falls, it makes a noise. Variation of that, a little treasure chest with a servo motor inside that opens as soon as they solve something. I can't tell you how many times the servo motors have been stripped open because I didn't tell the children beforehand, it'll open automatically, don't force it, because they always force it. We've got some really imaginative ones. So a sword that's kept in place with a maglock on the side, and as soon as the maglock releases, they can take the sword out and see whatever was on the side there. I can tell you my wife really loved this one. But she didn't love it nearly as much as I love the next one. This is, I think, the best way to dispense clues. I call it splinters in danger. And again, my wife says that I've got a very prototype aesthetic. I think she's been very kind because this looks like shit. There's a little servo motor at the bottom of the latch, and it keeps a string under tension. And when the servo motor releases, it flips forward, and it hits the plank in front, shooting off whatever you've put in the little contraption at the top. This is really great because it makes a lot of noise. And if you can put it somewhere where the players don't know that this is going to happen, and you have them solve the musical tone before, where everyone's listening very intently, and they're trying to solve the scene, and suddenly, bam! It gives them a great fright, and this thing comes flying through the air. I like to think that by terrifying the children, I'm teaching them that progress is scary, and achieving your goals is something that they shouldn't work too hard towards. So all of these devices have something in common, and that's how I interact with them. I use ESP. This is an ESP 8266. Most of the devices I used ESP32s, some of them 8266s. You don't really have to know too much about the difference. Ultimately, what these are these are little programmable computers, like Arduinos with Wi-Fi. And you can turn them into portable web servers. So you can have some code that runs there and says, well, when I get an HTTP request on this endpoint, return this response, or do something like that. So you could send a request through that says, well, when I send, you can make a HTTP request to the device that will then cause the device to open the maglock, for instance. The problem with this is that the way that this works is that there's a server.handleClient method. So this little loop method gets called over and over and over and over again. And the server.handle client just goes and checks, well, do I have any waiting HTTP requests that I need to respond to? And this is single-threaded, which means that in the happy path, what happens is you get an HTTP request into the device, and the device says, oh, OK, sure, here's your response. But it's not always going to work like that, because sometimes you might have other devices connected. So this is a digital spirit level. It's an MPU 6050. You don't really need to know about that. But some of these devices have digital motion processing on the chip, and some of them don't. And if they don't have it on the chip, you have to do that calculation yourself manually. So if your device is busy calculating the angle, it might take a long time. And if it's taken a long time and you get an HTTP request coming into that device while it's busy calculating the angle, by the time it manages to work out what the response is and finish calculating the angle, that HTTP request could have timed out. And as far as the client is concerned, that device is no longer working. This is a form of temporal coupling, where you've got, if you make the request at the right time, you'll get the response, but if you make the request at the wrong time, you might not. So ideally, instead of having this type of coupling, the better way to do it would be you'd have your devices sitting there, they would calculate the angle for whatever they need to do, they would take whatever time they have to do to calculate that angle, they would get the response, and then afterwards they would go and check, well, what do I need to do next? Maybe there's a database somewhere that's got a list of things that they have to do. Oh, I've got the angle here, the angle is this, so now I need to go and open that maglock or something. Now, because I work for particular software, we do a lot of messaging, so naturally I went for MQTT, which is a messaging technology. Stands for Message Queue Transient Telemetry, I think. And it's a really nice way of using messaging with these IoT devices because it's lightweight, so these low-power devices can work quite easily with MQTT. It's reliable, so you can specify 3 different levels of quality of service. You can do at most once delivery, at least once delivery, and exactly once delivery, which is pretty cool. It's also standards-based, so if you're working with a MQTT broker and one day you want to move to, I don't know, Azure IoT Event Hubs, you can just change and everything should work in theory because it is standards-based. But even though it's got the word queue in the name, it's not actually a queue, so there's a few downsides here. The queue length of MQTT can only be 0 or 1. You can't ever have more messages in a queue, which is weird for a queue. And it's got a slightly smaller feature set. But we'll take a look a little bit later at how we can work around this. So for my system, I had all of these devices, and they were communicating via Mosquito. Mosquito is an instance of MQTT. And that's all of the context out of the way. So now we're going to start getting into the microservice stuff. And the things we're going to look at are how I monitored it, how I decided what the aggregate routes are for these different components, how I managed the flow of the escape room, how I was able to change the difficulty of the puzzles as people were playing, and how to work around the limitations of MQTT. So those are the 4 things we're going to cover in the rest of this talk. Monitoring the devices. So the first thing that I did when I monitored the devices is I wanted to know about failures. When something goes wrong, I want to know about it. But the thing with these devices is that they're not really that good at this. So what happens is, if something goes wrong, yes, you can write C++ or Python or JavaScript on these devices, and they all have try-catch mechanisms in them. But a lot of the times, the libraries that you use don't really follow good citizenship when it comes to how to deal with exceptions. So oftentimes, the devices just crash and reset. And when the device comes online, you need to go and check, well, OK, why are you coming online? Did you lose power? Was it a watchdog timer that you thought I was taking too long to do something, so you just reset? Was it a hardware fault? Was it an exception? So you need to monitor all of these things. So then I thought, OK, well, what I'll do is, instead of actually going and checking the failures, I'll just see if the devices are online. So I'll include some type of health check API. And I can do that because it's just a web service. I'll have a /API/heartbeat. And as soon as it gets a request, it just returns a response 200 OK. I mean, that's fine. That works. I also thought, well, maybe I could look at the queue length. And as I started getting down the rabbit hole of this, it kind of became familiar to me. There was a bit of nostalgia to this. And I thought, hold on. This is reminding me of the way I used to monitor systems in the mid-2000s, where you had an application server and a database server, maybe a web server as well if you were really fancy. And the way you monitored these systems is you just asked 3 questions. Is the web server up? Is the database up? And can the web server talk to the database server? This is a very naive way of monitoring systems, and this is kind of what it was feeling like when I was trying to do these health check APIs on these devices, because it's basic. It's not giving me any insight. But the thing with these devices is they're quite small. You might even say they're like micro, right? And they provide a service. They do some type of capability. So maybe they're micro capabilities, not microservices. That's a rude word. Now, I know about monitoring distributed systems or microservices because that's part of my day job. And when you monitor distributed systems, there's 3 things you need to think about for everything that you monitor. The first thing that you need to think about is the area that you're monitoring. So what do I mean by the area? Are you monitoring the infrastructure of your application, of your system, or are you monitoring the application of your system, or are you monitoring the actual capabilities that your application exposes? Some example questions of this is, if you're monitoring the infrastructure, you might ask, well, are my devices online? For the application, you might ask, are my devices responding to publishers? Are they doing what they're supposed to do? And for the capability, a question might be, can my players solve the puzzles that I presented? Is that capability functional? So when you look at the monitoring area, you've got infrastructure, application, and capability that you can monitor. Next to that, you've also got the concern that you're monitoring. So by concern, what I mean is you could monitor the health of your system. Now, there's a many-to-many relationship between the areas and the concerns. You can monitor the health of your infrastructure, the health of your application, and the health of the capability. The same with the performance. You can monitor the performance of your infrastructure, the performance of your application, and the performance of your capability. And the same with the capacity. So those are the 3 concerns that you could monitor. And then the third thing with monitoring distributed systems is how you interact with those logs or those monitoring systems. Is it passive? Are you just looking at the log files every now and then? Are you just, okay, something's gone wrong, we need to look at the open telemetry for the system and see what went wrong? That's passive. You're looking at something after the fact. You could also do reactive monitoring, where maybe the monitoring system that you've got in place automatically detects, oh, this looks a little bit weird. I'm going to send a push notification to the ops team so that they can look at this before it becomes a potential problem. And then you've got proactive monitoring. So this is where the system would try and make changes to fix whatever might be potentially a problem. A good example here is auto-scaling. If the queue length is getting really long, maybe you automatically scale up other instances of your handlers so that you can bring that queue length down. So with this framework in place, let's take a look at what we were seeing with the IoT devices. So with the health check APIs, what I was monitoring was the health of my infrastructure, and I was doing it passively. Because I would just go and look, well, something's not working. Are they? Oh, yes, they're all up. It's fine. But if I was looking at the MQTT queue length, now, because the MQTT queue length can either only be 0 or 1, I know that if a queue length stays 1 for a really long time, it means that something isn't taking messages off of the queue. So again, I know that there's something wrong at an infrastructure level. The health of my infrastructure is suffering there. If I was looking at the failures, that would be, as soon as the device restarts, it goes and sends a message to say, hey, I failed because X. That is a reactive way of monitoring the infrastructure of the health of my infrastructure. Now, this is a lot of health infrastructure monitoring that I was doing. Am I getting new information from these 3 things? And the answer is not really, because there were times where the health check API was telling me that the devices were up and working, but the MQTT queue length wasn't changing, it wasn't ever decreasing. And what that tells me is that while the device is online and it's on the Wi-Fi network and it's responding to HTTP requests, it's not taking messages off of the queue. It's not processing messages. So the health check was actually a false positive. And with that information, I could then say, well, I don't actually care about the health check API anymore. Instead, what I can rather have is a dashboard or another tool that monitors all the queue lengths. And then I can immediately know if the devices are actually processing things. I could also have included canary devices. So maybe while the players are going through the escape room, I could sit and follow them and do a few decoy devices on the side to make sure that what was happening here would happen if they did it over there. And if I picked up a problem, potentially see maybe I need to turn the device off or non-reset it or something like that. That would be proactive monitoring of the capability that my application was providing. Let's take a look at some other examples, some non-IoT examples. So perhaps if you're monitoring queue length in a real application, that might be a good way to check the performance of your infrastructure. If the queue length is increasing, that means that the performance is potentially not enough and you need to scale up the endpoints. Or if the queue length is decreasing or staying constant, the performance is fine. Processing time. Processing time is how long it takes for a message to be processed once it gets taken off of the queue, so how long it takes your application to do something with that. That's monitoring the performance of your application. But of course, messages don't just exist as they're being processed, they exist in the queue as well. So combining queue length and processing time, we can get a metric known as critical time. And a critical time says, well, as soon as I send this message, the critical time of this message is however long it takes until it is processed completely. So that means it includes how long the processing time is, as well as how long it spends in flight, in the queue, waiting to get picked up. And you can use that to look at the capacity of your application, because that's a more important metric than just queue length. Queue length doesn't tell you how long things are staying in the queue. It just tells you how many things are in the queue, which is potentially maybe a problem, maybe it's not. If the oldest message in your queue is only there for 10 seconds, maybe not a problem. But if you've got a queue length of 5 and the oldest message in the queue has been there for an hour, potentially something you need to respond to. You can also use queue length to trigger scaling, and in this case, you would be doing proactive monitoring of the performance of your infrastructure. Like I said, it might be better to use a metric like the critical time or the processing time to be able to do that scaling, because you don't always just want to scale a queue that's got a lot of entries in it. So that's how you monitor distributed systems. You take the area, the concern, and the interaction type, and you can use that to see if you've got duplicate things, duplicate bits of information that you're getting. Because if you've got a large distributed system, there's a lot of monitoring information that can be presented at you, and you don't necessarily have to pay attention to all of it. So by categorizing which of these attributes you're monitoring and why, you can use that to potentially exclude noise from your monitoring systems, and then use that noise when you need to actually dig into what went wrong. So that's monitoring the IoT system. Let's take a look at the aggregate routes. I like using the musical tone as an example of an aggregate route because it is self-contained. It's a box on its own. Everything that you need to do is within that box, and it's a physical one. So for instance, all of the logic is self-contained. I can completely change the way that that musical tone puzzle works and is solved. Nobody else, no other puzzle in the entire escape room needs to know about that. The only thing it needs to do is that when the puzzle has been solved, it must publish an event that says, hey, I've been solved. That's all it needs to do. That's its only promise to the outside world. The only thing it needs to know from the outside world is when the difficulty changes, I need to change my difficulty either easier or harder, depending on what that is. So in this case, while it's a physical device, the service boundary, the aggregate route, is very well defined around this device. It's not quite so with something like Simon Says. So with Simon Says, where there were 3 boxes or 5 boxes or 2 boxes involved, what would happen is if we had another component that would have to change the difficulty of the puzzle, when it went to go and publish a message to say, well, we need to change the difficulty to 5, whatever that means, it sends a message to Mosquito, and then the devices go, okay, I can't make that decision on my own. I need to know what the other devices in Simon Says are doing. So we need to communicate together to be able to say, well, what do we do with that difficulty change? Which means that the boundary of consistency cannot be at this physical device level. It has to include all of them. So what we could do then is we could have a notion of a primary device. And the primary device would have secondary devices. Once they all start up, they would create a peer-to-peer network between each other, and only the primary has to talk to Mosquito, or MQTT. Then when the difficulty messages come through, that difficulty message goes straight to the primary device, and the primary device says, okay, everyone, we're only using the left button now, and the pattern is going to be me, you, me, you. And the other devices go, oh, okay, cool, got it, thanks. Move on. If something goes wrong with the primary device, maybe the battery runs flat and it disconnects, well, one of the secondary devices can take over, create a peer-to-peer network between the other devices that are remaining, and then subscribe to Mosquito, MQTT. So in this case, what this means is that the boundary of consistency of these devices, the aggregate route that we've got, is around all of them. Logically, there's only one instance of the devices, but physically they're deployed in multiple places. And the boundary of consistency has to be around all 3 of them. With all three of them in place, it means that the logic is self-contained, even if it is distributed across multiple devices. The logic within the service boundary can change completely. All they need to do is publish an event when the puzzle has been solved and subscribe to an event when the difficulty changes. So the service boundary is well defined around the three of these. Let's take a look at some more real-world examples. So maybe we've got a stock service, and a user is trying to delete an item from the stock system. And it says, okay, well, I want to delete this item, so the stock service will go to the authorization service and say, does the user have access to delete this record? And the authorization service will say, yes, they do. Go ahead, delete. The stock service has had to go outside of its service boundary to ask for information before it can do what it needs to do. It means that the logic is not self-contained within the stock service. It also means that the stock service needs input from the user service to be able to make a decision on what it needs to do. The service boundaries here, the aggregate root, is poorly defined. Another example, maybe if you're working in the insurance space, is anybody doing insurance? Maybe you've got a claims processing system, and the claims processing system would ask the payment system, hey, has the user paid all of their premiums? Again, it's going outside of its own system to ask for additional information. Or maybe you've got an order service, and the order service has to ask the stock service, hey, do we have stock of this item that I want to actually send to the customer? All of these are examples of where you're going outside of your boundary of consistency and you're asking for additional information. So the fix is easy, right? Well, all you do is if you need more information, just make your service boundaries bigger, right? And include all of those new things in your service boundary. Except sometimes that is the right answer, but ironically, a lot of the time you can make smaller service boundaries and get those boundaries of consistency even easier. For instance, if instead of a stock service that handled removing, you had a stock removal service that only did removal of stock items. The only thing this service does is remove items from the database. We don't have to worry about whether the user has the correct access to use this thing, because at a permission level, we can say, well, if you can publish a message to this topic, you by default have permissions to be able to remove items. It becomes an infrastructure concern, not a business rule check that we have to follow. So if someone can access that particular topic and publish messages to it, it means we don't need to ask, does the user have permission? And the important thing here is that we're doing something, we're not a something. So we're doing the removal of stock items. We're not doing stock service. Stock service isn't a thing. It's when users interact with your system, they're doing things. They are verbing your system, not nouning it. So in this case, the stock removal system only needs to know what it has to know. It doesn't need to know anything outside of just removal. It just needs to know, okay, the user wants to remove this thing, great. But what if you had slightly more complex business rules? So everyone can delete items from the stock service, or everyone can delete stock items, but only if they're below $1,000 in value. If it's more than $1,000, you need approval. Okay, well, you still have your stock removal service, and when the user removes an item, it publishes an event to the approved stock removal service. And that one approves it. So if the item being deleted is less than $1,000, it automatically approves it. Otherwise, it appears in someone's inbox, and they have to then go and approve that. Again, that service is only approving the removal of stock items. By making the service boundaries smaller and narrower, it's easier to get consistency boundaries, or boundaries of consistency. And the key thing here is that service boundaries are business rules. And by just hiding them away in stock service or policy service, you lose a lot of the richness of those business rules that you can use to make your systems easier to work with. The question might then comes up, well, if they're so small, if you're making these service boundaries so small, doesn't that limit you in terms of the workflow that you can do? We'll get to that next. So we've taken a look at aggregate roots. Let's say we've got all of our devices here, and we want to control the difficulty of the escape room. We want to make the room a little bit harder or a little bit easier as the players go through. Now, when I started with the escape room, I only had a couple puzzles. So it was easy. I could say, well, when they start this thing, just have a little timer that says, how long have they been working on this? Oh, it's been this long, so I need to change the difficulty and make it a little bit easier. Great, that was fine, until I started adding more puzzles. Because then what happened is, each puzzle has to keep its own record of, well, how long have they been doing this? Do I need to keep track of this? Which room have they finished? Which puzzles have they finished? Have they finished you? And the devices have to start knowing about each other, and they have to start asking, well, where are we? What can we do? And as you add more and more devices, it becomes harder and harder to do this and keep track of how things are working together. So I introduced the concept of an escape room run. And an escape room run is a state machine. So the way that this works is the players start the escape room. And immediately, as soon as they start, they are on schedule. The state of the escape room run is on schedule. They solve some puzzles, some time passes, and they're still on schedule for a while. Eventually, enough minutes pass that they are behind schedule. So the state has changed from on track to behind schedule. And at that state transition, my escape room run can start taking messages and publish them off to say, okay, now we need to make the room a little bit easier. Actually, I'm going to not have that puzzle in the room at all. They solve some more puzzles, they solve some more, and eventually they get back on schedule again. Maybe it's still too easy, or maybe we've left it too easy, so they eventually solve enough puzzles that they are ahead of schedule. So again, this is another state transition. So in this new state, we will again publish more messages to say, let's make the escape room a little bit harder. And eventually they solve more puzzles, time passes, and they get back on schedule. And the state transitions happens over and over again as they go faster and as they go slower around the escape room. And eventually they can complete the escape room from either of the states, either ahead, behind, or on schedule. So at a conceptual level, the escape room run is a state machine that does a few things. The first is it tracks how long the players are spending in the entire room, not on specific puzzles, although it can. And it adjusts the difficulty of the following puzzles based off of how much time they've spent already. And it can change the entire flow of the room, so it can completely take some puzzles out and say, well, we're not going to do those ones anymore at all. Or if they're going really quickly through, maybe reintroduce some of the previous puzzles that they did. But the key thing here is that the puzzles don't need to know anything about any of the other devices. All of the complexity around managing the flow is encapsulated within this state machine. The puzzles don't need to know that, oh, I'm suddenly not part of the thing anymore. They just don't become part of the room. It's kind of like an orchestra conductor. Someone who's sitting there and standing there, usually, and they're conducting the orchestra. They don't have to play the individual instruments, but they would say, I need more strings, I need less percussion over there. Harp, you're scratchy, get off, you're not playing for a while. And then as they start seeing how the audience is responding to their symphony, they might then bring the percussion back up, bring the strings down, put the harp back in. They control the entire flow and the pace of the orchestra. But the violin player doesn't need to know what the percussion people are doing. The violin player has just got their sheet music in front of them, their algorithm, and the cues that they get from the orchestra conductor. Now, while the orchestra conductor can probably play a lot of the instruments in the orchestra, they're also not doing that. They're just controlling how everything comes together. In code, there's 3 patterns we can use to accomplish this. There's the process manager pattern, and if we're in the .NET space, we typically call those sagas. There's the actor model, which you can also use, and there's the route and slip pattern. Now, the route and slip pattern is probably going to be a little bit harder to do than the other 2, simply because as you send that first message out to start your escape room, you have to have the full compensating flow included in that original message. But the key thing, or the fun thing here, is that the aggregate routes remain simple. The violin player doesn't need to know anything about anything else. The puzzles only need to know about their own little world. So those consistency boundaries stay the same. But because you've got this process manager, you can build some really complex workflow into your escape room. And the complexity is encapsulated, which means that it can be tested. It can be unit tested quite easily. You've got all of this complexity sitting in one class that just says, well, state transition. What happens when I transition to this state? What do I need to do? What do I expect to happen? Has it happened? Yes. Very easily testable. In a more maybe real-world scenario, you might have the claim capture service that publishes an event to say, hey, the claim process has started. A user has submitted a claim. That would go both to the Saga as well as to an assessor feedback service. And the Saga says, well, OK, I need something else to carry on with this claim, though. I need to know whether the assessor says that this is a valid claim. I need to know from the payment service that they've paid up to date. I need a whole bunch of information. So the assessor feedback service would go and say, well, the feedback has been captured. And maybe this is enough for the Saga to go and say, OK, cool, well, that means that the claim has been approved or rejected or something like that. So the claim capture service and the assessor feedback service only know their thing, but the Saga, the orchestrator, knows more and is able to piece those pieces together and send those messages off. which means that I've got my devices, and then to control the room, I introduced a escape room run, which was an implementation of the process manager pattern. And that then allows me to have the super small boundaries of consistency while keeping complex logic flow within my system. Now, in order to do this, I needed to work around some of the limitations of MQTT. So as we said, MQTT is not actually a queue, and it's got a slightly smaller feature set. The things that were problematic specifically for what I was trying to do was that there's no support for delayed delivery in MQTT. So delayed delivery is where you say, I want this message to only be sent or delivered to the endpoint in a month's time. For the escape room, it was going to be matters of minutes, not months. But there was no support for delayed delivery at all. There's also no support for time to be received, which means that if you get a message after it's expired, you want to be able to discard that message, where MQTT doesn't have support for that out of the box. And most problematically, you can't queue up messages. And because there's lots of things going on all at once in the system, there's a high probability that a lot of messages will go to my process manager, and it will lose messages because they'll be overwritten by other messages. And strangely, for something that's so ubiquitous, MQTT is surprisingly hard to monitor, which I found a little bit odd. What I would have liked is if I could have all of my devices talking to a broker that they were really good at talking to, and I could have my application logic, my complexity, talking to a broker that it was really good at talking to, and then maybe there was something in the middle that allowed the two to talk to each other. And this is where you implement the messaging bridge pattern. So the messaging bridge pattern allows you to have different endpoints on different queuing technologies, and it takes care of shuttling the messages backwards and forwards to where they need to go. And the two sides of the transport don't need to know anything about each other. So for instance, if I added another service that collected stats about my catapult, that wouldn't have to change any of the code on the devices side. All it would do is say, okay, well, I want to subscribe to that message in RabbitMQ, and the bridge would take care of saying, oh, that means I need to subscribe on MQTT and forward messages through. It's a super powerful technique. Now, the way that it works is that it would take all of your physical endpoints, so it would replace the sword with a logical sword, the essence of a sword, if you will. It would replace a treasure chest with a logical treasure chest, and it would go through all of the devices and change them. It would do the same with the application parts, and then the transports would also just be replaced with transport 1 and transport 2. So we're dealing with logical things. The bridge is the only one that knows, okay, transport 1 is MQTT, transport 2 is RabbitMQ, which means that when my Saga needs to send a message, it publishes an event to a topic on transport 2. The bridge knows, oh, hold on, that must actually go to the catapult. So it takes the message off of RabbitMQ, goes to MQTT and says, well, how do I transform this logical endpoint into a physical address? Okay, now I send it over there. Which also means that you can add additional functionality without changing the previous system. So you can add a new logical sword, and when your Saga publishes an event that the sword is interested in, the first one will go via RabbitMQ, and the second one will go via RabbitMQ MQTT to the original sword. This is a super powerful technique for doing things like modernizing legacy applications. If you've got a system that's talking MSMQ, first of all, my commiserations, that must be very hard on you. Second of all, if you've got the concept of, or an implementation of a messaging bridge, you can then, instead of having to make changes to your MSMQ system, deploy the bridge and start using newer, cooler technology, such as AWS SQS with Lambdas. And the MSMQ system doesn't need to know anything about the new technology. The new technology doesn't actually need to know anything about MSMQ. All of that routing logic sits within the bridge component and is able to take messages from one to the other. So if you were modernizing existing systems, what that would mean is you could slowly start taking bits of that system, moving them to newer technology, and the older parts wouldn't have to change. So you can use this to do step-by-step modernization of legacy systems. Super powerful technique. Right, so we've taken a look at how to monitor it. We've taken a look at aggregate routes, how we manage the flow of the escape room, and how you can work around limitations of technology. The question then becomes, well, how did it go? Well, here's good news. So it took a long time to get the whole thing assembled. Here is a picture of me assembling the balance puzzle. This was probably about the 5th or 6th iteration, and at this point I was convinced that I had all the kinks worked out, which is why I was using a new strip of LEDs on this one. It wasn't until a few minutes after this picture that I realized I forgot to re-include the holes into it so that I could get the electronics coming through the back. So we then moved on to iteration 7. The musical tone puzzle, I really wanted to have a little small profile, but I couldn't get the print strong enough, so I printed I don't know how many different versions of it, and eventually that's why it's now this big bulky thing that looks like it's a phone from the 1990s that my children have to use. I cut myself a lot on not just the sword, on lots of things. You'll also note in this picture that under the censored parts, that's where the fresh blood is, I have a plaster on, which means that wasn't the first time today that I had cut myself doing this. I'm not good at soldering things, so these 2 buttons need to go into these 2 holes, except you may notice that they're already soldered together, so I had to unsolder them. It was a lot of fun doing that because not only did I burn myself with a soldering iron many times, not only did I make many mistakes like this, I also melted the cable of the soldering iron with the soldering iron. And for those of you that like your clicky-clacky keyboards, I apologize, but I also melted 2 holes into my keyboard. It was not good. I am not good at soldering. But anyway, eventually I got all these pieces assembled and ready to go, and I thought, okay, now I'm excited. Let's get this. We'll get all my children's friends together, and we'll run this escape room. And it was exciting. You build something like this and you think, well, this is going to be great. It's going to be like the Colosseum. There's going to be these amazing Greek warriors coming in. And it's going to be great. Maybe it'll be like the movie The Goonies, where the children work together and they solidify their friendship and they come out better for it at the end. I didn't get that. I got this. They broke everything, absolutely everything. For the first attempt, it was painful, but I was happy with this. It was okay. It was a learning experience. The second attempt was the exact same thing. The third attempt was the same. Eventually, on the 4th attempt, this is a picture of me sitting outside afterwards in absolute despair. My dog is excited that I'm there with him, but I could not care at all for that poor animal at that point in time. And I distinctly remember after this picture was taken, one of my daughter's friends, she's an absolutely tiny little girl. She looks like she's about 3 or 4, but she's 5 or 6, and she's very sweet. And she comes up to me while I'm sitting there outside, and she puts a little hand on my shoulder, and she looks at me. And children are kind. Like, I don't know what it is about as we grow up, we lose a lot of that innate kindness. And this little girl, she puts her hand on my shoulder, she looks at me, and she says, maybe you should have tried harder. And the kindness stung for a long time, but eventually I did try harder, and we got all the pieces working together. So there's a few pictures of the kids doing some of the more physical puzzles. I included a lot of the physical puzzles at the beginning of the escape room so that at the end I could have more leeway with changing the IoT ones. So they solved the thing, they eventually managed to get it, and they opened the final crate and got their reward out at the end. And it was a lot of fun. But there's a few things that I remember from this experience. The first being that monitoring complex systems, even if it seems simple, must be intentional. These devices, it didn't seem like it was going to be a big system, but by thinking about monitoring it as a real production system, it was easier for me to identify what was important when I was monitoring it and what I could ignore. Service boundaries are business rules, and if you just ignore that, you lose a lot of value, and a lot of simplicity gets introduced when you embrace those business rules as part of your service boundaries. And distributing state allows you to keep the simplicity within the devices. Polyglot messaging can be super useful. Greg Young has a talk about polyglot databases. I suppose this is polyglot messaging, which is quite fun. But for me, the most important thing that I got out of this, and that will stick with me for a very long time, is what it did to my children. My daughter on the left here is building her own little escape room at my parents' house. And it was because she had so much fun eventually doing the escape room that I did for her. My daughter on the right, one of the other puzzles involved a magnifying glass. So from magnifying glasses, we got to binoculars, and binoculars then became telescopes. And now she makes me take her to stargazing camps so she can look at the stars in the skies. The experiences that I've created for these children was more than what I initially anticipated. So when you go through the rest of NDC Oslo tomorrow, don't just sit and absorb some of the learnings and the technologies and the techniques for the rest of the conference, but also think about what else could this potentially unlock for me in the future. Thank you very much. I do have time for questions, but I'd rather just meet you outside and you can chat to me there. If you want to come to the particular booth tomorrow, you'll see a few of the escape room puzzles sitting running there, so you can also give them a bit of a go if you'd like. Thank you.